Welcome, my friends, to a conversation on conservation of energy. Today, we're going to be talking about kinetic and gravitational potential energy, as well as the general principle of conservation of energy. And we'll list some common types of energy so as we talk about things, we can talk about them in a common language. You've learned about conservation of energy before, especially freshman year, as well as probably in the middle school, and in terms of in biology and in chemistry. We've also learned other conservation principles such as conservation of mass and conservation of momentum. We'll find that they all have the same basic idea to them. Let's get started. First of all, I'll talk about kinetic and gravitational potential energy. We'll move pretty fast through this because this is a review for you guys. Of course, kinetic energy is the energy of motion, which means that all moving objects have the ability to do work, because having energy is the ability to do work. So if you have kinetic energy, you can do work. The equation for kinetic energy is straightforward. You've seen it before. It is Ke equals 1/2 mass times velocity squared. Now, of course, this v squared part is unusual. We always see it in science, but it's not incredibly common. V squared really means v times v, of course, so we can write this as 1/2 mv times v. So you can see we're multiplying v in there twice, and that's what happened to the squared. Not doubling it, but multiplying it twice. Big difference there. And of course, the two variables that affect kinetic energy are mass and velocity. And as we increase the mass of an object, its kinetic energy gets bigger. As we increase the velocity of an object, its kinetic energy also gets bigger. So both of these variables increase your kinetic energy. Now let's talk about the relative effects of mass and velocity on kinetic energy. So I'm going to write up here again our equation, Ke. And I'm going to write it out in the sort of long format, without the squared. So 1/2 m times v times v. Those help us see a little more clearly what's going on here instead of the squared. But of course, this is the exact same thing as writing mv squared. The squared here is just a simplified shorthand for this. It's just to be lazy a little bit. So we can see here, as we increase the mass, we increase the kinetic energy. But what if we were to exactly triple the mass? If this number suddenly got 3 times bigger, that would mean this whole side gets 3 times bigger. So tripling the mass triples the kinetic energy. Now let's do the same thing for velocity and see what happens. If we triple the velocity is in the equation twice here. So if we triple it, we're tripling this one, but we're also tripling that one. So both of them get tripled. And a triple times a triple is 9 times the kinetic energy. So because this velocity shows up twice in here, multiplied twice, it's going to have a greater impact. Its impact is going to be squared on kinetic energy. So unlike mass, where tripling the mass triples the kinetic energy, tripling the velocity gives you a 9-time increase in the kinetic energy. That's incredible. It's also why it's so dangerous to drive fast. Now let's talk quickly about gravitational potential energy. So energy that is stored due to an object's height and weight is what gravitational potential energy is. So the higher you are, the heavier you are, the more gravitational potential energy you have. The equation, of course, is Pe is equal to mass times g, this is the gravitational acceleration, times h. Now there's two ways to look at g. G is equal to, of course, 9.81 meters per second, and that's the way we looked at it so far. It's the acceleration due to gravity. But there's another way to interpret this number, and that is g is equal to 9.81 newtons per kilogram. Now if we look at these units, a newton is a kilogram meter per second. So if we break Newton out, we end up with kilograms canceling, getting meters per second, the exact same thing as this. But here's a different interpretation. This interpretation is the acceleration due to gravity. And I should say here probably due to the gravitational force. Right? And this interpretation is slightly different. This is the strength of the gravitational field. I'll show you how to interpret that number. So it's the strength of the gravitational field. Here's how that makes sense. What this number tells us is that for every kilogram of mass, I'm going to get 9.81 newtons of gravitational force from that. So it gives me the ratio of mass to weight, and that gives me an idea of how strong the field is. The bigger this number is, the more weight I'm going to get per kilogram. So if this number was 23.7, that means I would get a lot of force every time I had a kilogram of mass. So there's two ways to approach this number. And as we look at it with PE, it's typically more convenient and more helpful and insightful to look at this as a number that tells us the strength of gravity. It tells us how many newtons we get from a kilogram. Okay, so that's the potential energy equation. So the variables that affect potential energy, of course, are going to be mass, gravity, and height. We may have left height off this one. Okay. All right, move on to the next slide. If you need more time, just hit pause. No biggie. So conservation of energy. The main idea of conservation of energy, just like mass and just like momentum, is that energy cannot be created or destroyed. Energy can be transferred or converted to other forms, but it has to come from somewhere and it has to go somewhere. Hey, it's this last point that's going to concern us this most. It has to come from somewhere and go somewhere. I'm going to see if I can highlight that. I've not done this before, so maybe I'll be good at it, maybe I won't. So it has to come from somewhere and go somewhere. That is a really key idea. It doesn't look good at all. I apologize. Let me erase that. So as we go through this and we're talking about conservation energy, keep that in mind, that whenever we're talking about the energy transfer, something doesn't gain energy by itself. Something else had to have lost energy for it to gain energy. And we'll talk more detail about that. An example let's look at is you shoot an arrow directly into the air, right? So as you do this, you pull the bowstring back, right? So you grab the string, you pull it back. When you're doing that, you're applying a force and going a distance. That's work, and that took energy. You are now more tired. Now, the energy that you used to pull that string back had to go somewhere. And the reality is the energy, most of it, goes into the stretching and bending, flexing of that bow. So that energy is stored in the bow is what we call elastic energy, because that bow can snap back. So you pull it back, stretching it. When you let go of the string, the bow snaps back. And when it does that, the string pushes the arrow, doing work on the arrow. So that elastic energy in the bow is being converted by the work. It's being converted into kinetic energy of the arrow. All right, let's catch up a little bit. Now, as that arrow shoots straight up in the air, right? So the arrow's going up. As this goes up, it slows down, losing kinetic energy, but it simply doesn't lose the energy. It converts it into potential, gravitational potential energy, because it's getting higher and higher and higher and higher off the ground. I'm going to move on to the next slide. So as the arrow travels up, it starts to slow down. Whoops. Starts to slow down. And we see, so at this point, right, we have a little arrow here. It has, its potential energy is 0 because, well, let's do that the other way. Let's start with the reason and then go to that one. Its height is equal to 0. Therefore, its potential energy is equal to 0. And the kinetic energy is equal to some number. So let's just make up a number and say the kinetic energy is equal to 200 joules. It got launched really fast, right? So the arrow is going to go up and come down. It was shot straight up. I'm just going to put this little curve here so it won't be right on top of itself. So let's look at the halfway mark, right about here. Oops. And it comes down and sticks into the ground. So at the halfway mark, our arrow is right here. And now it's gone up, it's lost actually half of its kinetic energy. So at this point, its kinetic energy is 100 joules. And at the halfway point, it's lost that 100 joules of kinetic, but all it's done is really turned it into potential as 100 joules of potential. So notice the total energy here, 200 joules total, is equal to the starting total energy, 200 joules. At the top here is this arrow is like this, and it's flipping over and coming back down. Its kinetic energy is equal to 0, and that's because the velocity at the top is equal to 0. Now remember, that velocity at the top is equal to 0. It doesn't stay at 0 for any amount of time. It passes through 0 from its way on the positive velocities to negative velocities. Here, the potential energy is at a maximum because it's the highest point up. So its potential energy is large. In fact, it's 200 joules. It's now converted its kinetic energy into potential. On the way halfway back down, we find the same thing as over here, is that it's lost half of its potential energy, is 100 joules, and the other half is kinetic energy, which is 100 joules. Now this is a really simplified version. Oh, and then at the bottom, the same thing happens. The kinetic energy is all the way back. It's moving super fast. Its height is 0. That energy has been conserved. Now in reality, what happens is this arrow has to push through the air. So it actually loses some of its kinetic energy, not just a potential, but also to all the pushing through the air. So these numbers will be a little bit smaller here for the potential energy conversions, but they'll also be made up somewhere else. That energy has to go somewhere, and we'll talk about in a few minutes, but that somewhere is going to be heat with the air. It's going to heat the air as it pushes through it because it bangs into those air molecules and speeds them up. Okay? So here at the top, all the kinetic energy is gravitational potential energy, and then it converts gravitational back into kinetic. Everybody say hi to Kim. Hi, Kim. Say hi, Kim. Kim's video shy. You have to forgive her. She's trying to do some laundry. All right. Whoa, that came up a little fast. Well, let's just leave it there and see what happens. So on this slide, we're going to get a little more mathematical. And so the conservation of energy really boils down to this first equation. E before equals E after. And for our arrow, what that means, is that the kinetic energy plus the potential energy before is equal to the kinetic energy after plus potential energy after. So the total energy before equal to total energy after. These sums are always the same. Now, the amount of kinetic and potential can vary, but the total of them before has to equal to total after. And we'll look at it in our arrow example we just gave. This one was 0, right? And if our after was the highest point, then this one would have been 0, and the kinetic energy before is equal to the potential energy after, as it did that conversion, right? If we're going from ground level to the top, but you don't have to do that. You can go midway to 3/4 of the way. It always works. They're always equal to each other. All right, let's move. So let's put it to use. So we've got this helicopter here, and it's got a car attached to the bottom of this helicopter, and this car is 4,000 feet above the surface of the earth, and it's a bad day for the car because, as you probably guessed, they are going to drop it. This is a Mythbusters episode. They're going to drop this car and let it smash into the ground. So the question here is, how fast should the car be traveling when it hits the ground? Let's look at it. So if all we look at is we try to find some velocity equation, this is going to be really tricky. But if we start with energy, it becomes easy pretty fast. So we know that E before is equal to, E after. Right? My energy before, the car is not moving, it's stationary here. The energy before is simply the potential energy of the car. I'm going to put a B here for before. And this, when it snaps, it's going to fall down to the ground. And right as it hits the ground, its height is going to be 0. So here's my car, a billionth of a second before it hits the ground. Its height is 0, so its potential energy is 0 now. And it's converted all that potential into kinetic. And I really should write it this way. I'm going to write it more formally. So this is the before, the kinetic energy, potential energy. Kinetic energy of the car after plus the potential energy of the car after. Right? And here actually, since all these things are car, I can leave these guys out. That was excess. Now to start with, the kinetic energy is 0 because it's not moving. V is equal to 0 meters per second. At the end, the height is going to be equal to 0 because the end is down here at the bottom. So this is going to be 0. So now we find that the potential energy of the car before is equal to kinetic energy of the car after. So let's plug it in. PE before is equal to the kinetic energy after. And let's put some equations in. So this is 1/2 mv squared. This potential energy before is mgh. Now notice something interesting happens here. The masses cancel out. Right. So I'm left with gh is equal to 1/2 v squared. If I'm trying to find the velocity here, and of course this is the velocity at the bottom after, right down here, I need to multiply both sides by 2. So I find that, and then take the square root of it. So I find that v is equal to 2 times gh, and this would be v squared still, so we square root it. Square root of 2gh. Now notice this is extra information in the problem. It wouldn't matter if there's no air resistance. It doesn't matter if it's what the mass is. It's going to all fall the same and hit with the same speed at the end. So that's a neat thing to see. So now I just plug in numbers here, and I say that, hey, 2 times g, I'm going to cheat and use 10 newtons per kilogram. And if you want to put meters per second here, it's the same units. And then the height is 1,219 meters. When I do this on my calculator, I get a number, I don't know. It's a fast number. Let me do it real fast. 20 times 1219, square root that, 156 meters per second. Now in reality, this car does not hit at that speed. There's air that's getting in the way and slowing it down. And as that car bashes through the air, it knocks the air out of the way, speeding the air up. So that energy difference between what it should have hit with that we just calculated and what it actually hits with, that's going to be the amount of heat generated in the air on its way down. So if you were to take a nice thermal camera video of the car falling, you'd find the air behind the car is a little bit hotter than the air in front of the car. All right, hang on, we're almost there. Conservation of energy, second example problem. The other really cool thing that we can do with it is we can find this maximum height problem. So we have a bowling ball here. It's fired directly into the air. So it's here, boom, it's fired up into the air. And we're trying to figure out how high it can get. So right here is our height, and that's a question mark. We know its velocity at the bottom is 25 meters per second. And the height down here, we're going to call this height equal to 0. Right down here at the bottom. We can decide where the height is 0, and might as well do it there. Again, we're going to use energy here. Energy before is equal to energy after. So I know that the KE before plus the potential energy before is equal to the kinetic energy after plus potential energy after, potential energy after. Now to start with, my potential energy is 0 because my height is equal to 0. I have kinetic energy because I have some velocity. And on the top here, my velocity is equal to 0. So that is equal to 0 because my velocity is equal to 0. That means the kinetic energy before at the bottom is equal to the potential energy at the top. So as I write this out, I'm going to say 1/2 mv squared before is equal to mgh after. And that after in this case is the very top of the flight. So again, I notice that the masses cancel. And if I solve here for h, I have to divide both sides by g. And I end up with h is equal to the 1/2, so the 2 goes in the bottom, v squared over 2g. That's the maximum height that it can reach. Now, velocity starting with, now of course, is velocity before. The velocity before is 25 meters per second squared divided by 2 times, and I'm going to use 10 again, newtons per kilogram. And I'm going to find the answer to that one. 25 times 25 divided by 2 divided by 10. 25 times 25 divided by 2 is 31.25. So I'm going to round that to 31.3 meters. And that is this guy. That's the total height, 31.3 meters. So you can see using energy can simplify some problems enormously. And it's why we think about energy when we do problems in physics. We think about physics is because it allows us to, gives us a really strong framework to think about problems and figure out what's really happening in the world. It's super cool. We'll work with a bunch. All right. Now I'm going to go through these slides really quickly. I'm going to list a whole bunch of different types of energy. I think 7 altogether. So you may want to listen as I go through them, and then at the very end of the slide, write down the key information from the slide instead of trying to keep up with me as I go, because I'll be moving kind of fast. So elastic potential energy is stored energy from anything that's stretched out. So when you're wearing elastic waistbands in like your shorts or sweatpants, you stretch them out and they can snap back later. That's elastic energy. Rubber bands do this. Springs do this. The suspension in your vehicle does this. Anything that flexes and snaps back, a mouse trap, a bow, when you kick a football or a soccer ball or any kind of tennis rack or a tennis ball, all those balls get compressed and then they spring off your foot. And that compressed part is the elastic potential energy. Great. The next one's thermal energy, and it comes from the random motion of atoms. You know that heat, thermal energy, is a result of atoms moving faster. In fact, the only way to heat something up is to make the atoms move faster. Chemical potential energy is any energy stored inside of the bonds between atoms in a molecule. This includes food, batteries, gasoline, anything that burns. So if you light a campfire, the heat you're feeling used to be chemical potential energy stored in the log. Anything living, it's their life source or their energy source for living things. Anything that's, I think that covers it. Awesome. Nuclear potential energy. This is a strange one, so we don't see an example of this very often, except for one major way. But this is the energy released when we convert mass directly into energy during a nuclear reaction. This is not the kind of things that happen in your body. These things happen at nuclear reactors, nuclear bombs, and the sun and all stars are examples of this kind of conversion of energy. It's a huge conversion, but it's hard to get the nucleus of the atom to break apart and convert some of its mass into energy. That's that. All right, so if you want to write this down, pause the video now. Now, if you want to write this down, I mean you don't have to write down. You need to write down. All right, here we go. So radiant energy, this is energy that's light. So light, microwave, cell phone, lasers, any kind of signal that you send across space is radiant energy. The heat you feel from the sun reaches the earth as radiant energy, so it travels as light to the sun, and it travels as light to the earth from the sun. So anything light-based is going to be a radiant energy, or heat-based that travels through the air. When you feel the heat radiating off of a fire, it's radiant energy. It's coming to you as light. It's infrared. So sound energy, so sounds do this. So whenever we vibrate air, of course, we get sound. And that vibration of the air is a type of sound energy. Electrical energy, this is the energy of moving electrons. It's in the wires and power lines. Batteries convert their chemical energy that they store the energy as into electrical energy as they push electrons through the wire. But when it's stored in there, it's not stored as electrical, it's stored as chemical.